Okay, welcome. I think this is the last colloquium of the semester, and it's a pleasure to introduce our speaker, Piers Coleman from Rutgers University. Piers did his undergraduate work at Cambridge University in Trinity College, and then he went to Princeton and to do his PhD, and he became a postdoc at the ITP, the Institute for Theoretical Physics, before it became the KITP. He's, as I mentioned, currently at Rutgers, but he's also at the University of London at the Royal Holloway School, where he spends a month each summer. So many of you graduate students know Piers from his textbook, Introduction to Many Body Physics, which is probably the most comprehensive textbook about modern topics in hard condensed matter physics. And in fact, I saw him just a few minutes ago personalize a copy. So if you have your copy, you can bring it down and Piers will sign it. So Piers has been involved with many facets of condensed matter physics, starting with the Kondo effect, looking at heavy fermion systems, high temperature superconductivity in general, magnetism, and topological systems, strongly correlated electrons. He's made contributions to many, many of these fields. So it's a real pleasure to hear him today talk about dark matter challenges of the solid state.
Thank you. Okay, can everyone hear me? Is that good? Okay. Good afternoon. I'm honored to be your last speaker of the semester. Is that too loud? Is that good? Okay. So today I'm going to tell you about dark matter challenges of the solid state. I'm not going to talk about black holes, but I'm going to try to share with you why I believe that the quantum revolution that began 90 years ago is as vibrant and as challenging today as it was then, and moreover, why physics in the lab and physics in the cosmos are as intertwined as they were 100 years ago, and how there's still stuff to be learnt from this wonderful connection between the two. And lastly, how the physics of reductionism and the physics of emergence are as intertwined as they have been for a long time. And along the way, I'll also tell you about some of our ideas, trying to understand how something called fractionalization can affect order in exotic quantum systems. Okay, so let's see how this clicker works. Good, okay. Not that well, but that's all right. Okay, so these are various people who've worked with me both recently and in the past. I particularly want to highlight postdoc at Rutgers, Yasha Komijani, who's done some of the work on fractionalization that I'll mention earlier, but also many other collaborators, in particular Po-Yao Chang, Ona Erten, Alexei Svelik, my partner Premi Chandra, Anna Toth, who's a physicist gone into finance at the Technical University of Budapest, and Ari Wugalta, who's a student at Rutgers. Okay, so what are we going to talk about today if this display works? I'm going to give a little discussion of history and remind you about some of the early signs of the quantum age. Why is that important? Because some of the things we can't understand today are early signs of quantum age 2, which is yet to happen, okay? And I'll tell you about the in-the-lab challenges that we have, which are the dark matter challenges of the solid state. And then, depending on how fast I'm going and how well you interrupt me and ask questions, which I encourage, I'll turn to talking a bit about a concept of order fractionalization, which is our attempt to gain perhaps some new insight into exotic quantum phases of matter. And then we'll have a conclusion. Okay? Okay, good. And just in case you can't catch this today or you want to look at it again, these are the ways you can catch it again. There's a PDF file on my website at Rutgers. I uploaded it to YouTube. This is the archive of the order fractionalization paper, which somehow exotically has 6 ones in a row. I don't know why that is, but anyway. Okay, so I want to remind you about the link between the laboratory and the cosmos. And I love looking back at the history of science because science is a very artistic endeavor, which means that you spend large amounts of your time being depressed on your lack of progress. So I find it very encouraging to think back at the historical stories and the difficulties people had in the past. And so I want to share that with you. And I want to remind you about how, first of all, according to the apocryphal story, Newton had insight into the origin of the Keplerian model of the universe by thinking about the way apples fell. And this is, although it's an apocryphal story, it does illustrate my point, which is that physics in the lab and physics in the cosmos are linked together. And another example I want to remind you about is the physics of the levitating superconductor. Superconductors levitate because photons traveling through them acquire a mass, and this keeps out the magnetic field. This discovery was the origins not only of understanding why superconductors can levitate, but also the origins of the understanding of how gauge bosons can acquire mass. We now call that the Anderson-Higgs mechanism. Okay, so let me remind you of a few early signs of the quantum age. Okay, one very obvious: why do hot things change color? Why is matter so hard? Why does the sun shine? These were very simple questions which physicists at the end of the 19th century couldn't answer, and they were mysteries that became early signs of the quantum revolution to come. Let's remind ourselves how these were solved. Okay? Why do hot things change color? Well, this led to the concept of blackbody radiation, the physical mechanics of electromagnetism, and the discovery of the photon. And this huge class of characters was involved in this discovery. Some experimentalists, some theorists. Rayleigh, a theorist, and Boltzmann, a theorist, and Planck, a theorist, and Einstein, a theorist, but Vienne and Kirchhoff, experimentalists, very much involved in establishing the phenomenology of blackbody radiation. Okay? And of course, today we know that blackbody radiation, which you can measure in various different ways, even by looking at the radiation out there, the blackbody radiation in the cosmos, has a peak at the characteristic energy of a thermal photon, when h bar omega is equal to kBt. Okay. What about why is matter so hard? Okay, we live in a very hard world, and we don't often stop to think about why matter is so hard. But it's not just because of Coulomb interactions, which are the only forces between particles. It's because of the statistics of the particles that are involved. Okay? The understanding of why matter is so hard grew out of the study of atomic emission lines, leading ultimately to the Pauli exclusion principle, which is the origin of hardness and chemical diversity. Here's a picture of young Pauli, and he, as a young man, was enraptured by the discovery of the Bose-Einstein condensation phenomena and the discovery of bosons. And these were the first particles for which statistics was properly understood. And physicists loved to go with the rage, and so everyone thought that electrons were probably bosons. But he realized that one would have to, if one extended his idea of the Pauli exclusion principle from just an atom out to the vastness of a metal, that he could understand the paramagnetism of metals. And in fact, this is a translation of his note to Schrödinger in December 1926. He was actually, with a heavy heart, he was saddened by the fact that electrons behaved according to Fermi-Dirac, not Einstein-Bose statistics, and he wrote one of his only papers on solid-state physics, the note on the paramagnetism of metals, the fact that when you apply a magnetic field, metals are not diamagnetic, but they develop a magnetization in the direction that you apply a field. But unknowingly, he had actually explained why matter is so hard. Because the Pauli exclusion principle is the reason that matter is hard. Because when you bring two atoms together, what happens is that you form bonding and anti-bonding states, but the electrons are forced to go out into the anti-bonding states as you bring them close, the matter close together. And as a result of that, you get a strong repulsive interaction. And at the heart of this is the fact that no two electrons can go into the same quantum state, a feature that's encoded in many body physics through the anti-commutation of the Fermi, of the creation annihilation operators. Okay, so when you jump up and down on the ground, just think that you're actually probing the exclusion statistics of electrons, and that were electrons bosons, it would have been a most unfortunate event. You wouldn't have even been there reading the fact that they were bosons, because were electrons bosons, every atom would be the same. All electrons would go into the 1s state. There'd be no periodic table, and matter would be sludgy and would just collapse, typically. Okay? So all of this out of one line of discussion. Okay? And lastly, why does the sun shine? Okay? We are fortunate to live orbiting around a star in the sweet spot, and our world has had 4.6 billion years of continuous sunshine. Okay? But the reason it's so gradual and so constant is because of the weakness of the weak interaction, which governs this crucial part of the helium cycle, the fact that helium atoms can break up into deuterons, an electron and a positron and a neutrino, is governed by the weak interaction, which converts a neutron into a proton, I guess, right? And so why is that interaction weak? Well, it turns out that the short range of the electroweak force and the Meissner effect share a common mechanism. A gauge field acquires mass, and this mass is converted then into a characteristic length scale. So in a typical superconductor, the London penetration depth is the length over which a magnetic field can penetrate inside that superconductor. It's typically of the order of 1/10 of a micron. Okay? If you compare that with electroweak, the electroweak penetration depth can be worked out from the mass of the W boson, is about 10 to the minus 18 meters. It's 10 to the minus 11 times smaller than the penetration depth of a photon inside a superconductor, but the physics is very similar. And you might ask, well, then what's the mass of a photon inside a superconductor? Well, you can work it out. If you look at this little formula here, you can see that lambda W times mW, the same formula will hold for a photon, so they're a constant, and so let's put that in. And let's then derive the fact that the mass of the photon will be equal to the mass of a weak boson, which is 100 GeV, roughly speaking, times this ratio 10 to the minus 11, and that comes out to be about 1 electron volt, which is the energy of a transverse plasmon, the energy of a photon inside a superconductor. That's what expels it. That's what keeps, in some sense, keeps this magnet levitated on the surface of the superconductor. This is actually the superconductor here, and this is the magnet there, I think, in this particular configuration. Okay, so the message of all of these, this little diversion here, is that we can learn a lot from physics in the lab. And each of these cases, laboratory-based studies were used to reveal deep, new concepts that apply equally to the laboratory and to the cosmos at large. And of course, that principle ended 100 years ago and doesn't apply today, okay? Or maybe not, right? Okay? So what can we learn about the cosmos from studies in the lab and vice versa? Presumably, things continue today as they've always done, that we can learn general principles that work in both places. Okay. And before I continue this diatribe, I wanted to remind you about the relationship between the different fields of physics. And these are some of the subfields that are at your lab and at my lab: astronomy, high energy, condensed matter, biology, biological physics. And on the one side, we have these discoveries that tend to attract the public attention. These are the large-scale discoveries, the high-Z search that led to the discovery of an accelerating universe and dark energy, the discovery of gravity waves, the observation at LIGO, the Higgs boson, and the prediction of the string multiverse in M theory. Okay. These are all examples of a reductionist approach to physics. The idea that really keeps physics going, the idea that comes from atomism, the idea that we can understand nature by learning the laws that govern its smallest components. That's very important in physics. You can't give up on that principle. On the other hand, when we start to think about putting things together, interesting things happen when we put together atoms. We get chemistry. The periodic table, of course, at this level can be understood in a reductionist way from the physics of the hydrogen atom. But when you start to put atoms together, you get chemistry in all of its diversity, and out of chemistry, of course, comes biology. And it's very interesting to think about length scales here, because quantum mechanics for us really lives somewhere around the angstrom scale. And our world begins somewhere around the micron scale. In a machine shop, you can machine things down to 1 micron. Of course, we have nanotechnology, which takes us down further, but our human world ends around a micron. Okay? And yet an angstrom is roughly the size of an atom. Okay? Let's think about this, the largest quantum objects we understand well at the moment. For example, a Cooper pair. In tin, the coherence length of a Cooper pair is about 230 nanometers. So those Cooper pairs extend out to about 1/4 of a micron. Okay? Interestingly enough, the smallest self-reproducing organisms are the same size. This is a picture of an organism that lives inside your gut. It's Mycoplasma mycodes, and in its smallest form, it's about 250 nanometers across. Okay. And whilst we very well understand Cooper pairs in tin, we barely understand the physics of mycodes, Mycoplasma mycodes. Okay? And so this is an example of emergence. It's the other side of the coin. And we're really interested in what are the principles that govern the emergence of collective behavior in matter between the angstrom and the micron. And lest you think this is an immense gulf, remember that in length scale it's only 4 decades, okay? And yet in those 4 decades life evolves, okay? So emergence is clearly a major aspect of our goal of trying to understand the world we live in, okay? And so it's very important to realize that there's a tension between these two things, emergence on the one hand and reduction on the other. And I went too fast there, or I can go back. I probably can't go back. Oh, it keeps switching. Anyway, so, and this tension between the two areas, the two approaches to physics, is very, very important. And you can't neglect one for the other. It was important to study an emergent phenomena to understand electroweak theory. It was important, by the way, to understand heat in order to understand the concept of energy. Without the concept of heat, the idea of energy was not possible. And so even though, in principle, energy conservation is a consequence of Newton's laws of motion, Newton didn't know anything about energy, nor did Lagrange, nor did Hamilton. It wasn't until the middle of the 19th century that energy was understood. You need to understand emergence to understand reductionism. Okay, so if we look at today, of course, dark matter is an iconic example of a major unsolved problem in physics today. Here's a nice picture of gravitational lensing by dark matter around the Abel cluster, taken with the Hubble Space Telescope. And of course, we now know that only 6% of the universe is composed of the matter we know and love, of baryonic matter and leptonic matter and photons. And 24% of that is dark matter, possibly some other form of baryonic matter, superpartners or something like that. And the other 70% is something even more mysterious, quintessence. It's a kind of energy density. It's part of the maybe part of some kind of zero-point motion of the underlying universe. And so this is a measure of our ignorance of the universe we live in. It's a major, major unsolved problem, and it's a major challenge to 21st century physics. You can't imagine that solving this problem won't transform the way we see the world in a fantastic way. okay? But as I'll try to explain to you, there are equal counterparts to that in the physics in the laboratory that we don't understand at the moment. And an iconic example taken from condensed matter physics is the linear resistivity of a cuprate superconductor. Here is some of the original data taken by Hide Takagi in 1990. And it's beautifully linear. This is probably lanthanum cuprate, strontium cuprate, and it's linear from 1,000 Kelvin down to the TC of the system. You can make this stuff in a microwave at home, and you'll get a resistivity that looks like this. But what's peculiar about this resistivity is that we would normally expect it to level out at some temperature where the mean free path of the electrons becomes comparable with the wavelength of the electrons. There's no leveling out at all here. It's as if the high temperature behavior, which should be linear, continues all the way down to low temperatures. And we don't understand the mechanism of this linear resistivity. And that means we don't understand the metal that gives rise to high temperature superconductivity. Okay? So we don't understand the fabric from which the pairs are born. Okay? But there are other examples. This example tells us that we have a breakdown of our fundamental theory of metals, the Landau Fermi liquid theory. Okay? Here's another example, which I will get to later today, which is of interest here at Brown University too. This is samarium hexaboride. It's an insulator which has a very, very small gap, discovered in the 1960s. And here you see the resistivity coming up and having a plateau here at very low temperatures. This plateau is now understood as the consequence of a topological insulator. And this has been a subject of great interest. But what's really weird about this system is it seems to also have a Fermi surface. It displays de Haasman-Alfvén oscillations, which are characteristic of electrons with cyclotron motion being quantized. And these are the Fermi surfaces that have been determined from the de Haasman-Alfvén measurements in this system. Okay? And yet it's a very good insulator. Okay? How can you have Fermi surfaces in a very good insulator? These and many other examples suggest the potential for qualitatively new advances in our understanding of quantum matter. Okay? Advances which presumably require a conceptual change in the way we understand our physics. Okay? And since these are quantum systems, it means that we have to understand some of the emergent properties of quantum mechanics in a better way. Okay? And there are other examples I want to briefly tell you about. One of the things that I should remind you about is that, of course, discovering exotic materials involves exploring the periodic table. In a way, quantum mechanics and the exclusion principle and the fact that 1 + 1 does not equal 2 in quantum mechanics because of interference, okay, means that when we put matter together, we get a great diversity of physics. And the periodic table is really the backdrop for that diversity. In fact, each new material is like a new universe. So this is our multiverse, in fact, the periodic table. But where should we look in this vast fabric of possibilities? Well, one idea is that we should look at those materials which are on the brink of localization. And you'll notice this is not a conventional periodic table. It has the d orbitals and the f orbitals organized in order of increasing localization. And so going up and going across, you get more and more localization. So these elements up here, the f electrons and d electrons typically localize to form magnets. These elements down here, the d orbitals typically delocalize and form conventional superconductors. But at the crossover between the two, at the point where electrons are on the brink of localization, interesting things happen. And we don't understand this localization physics at all well. Okay? One of the things that happens is that we get this strange metallic behavior. Here's another material, cerium cobalt indium 5, which is a miniature high temperature superconductor. It'll never be used in practical applications, but it's certainly very useful in experiments because the lower TC mean that you can manipulate this system without using colossal magnetic fields. Okay? And this system also displays a beautiful linear resistivity along the c-axis with almost zero intercept. And here is the resistivity in the AB plane. It's linear, and then it has a crossover to a t to the 3/2 behavior. Okay? And this is a very different but quasi-two-dimensional material that goes superconducting. Both are examples of strange metals. Okay? Here's another point that I wanted to bring to your attention. When you tune from one universe to another, you have to go through a black hole. But in material physics, when you tune from one phase to another, you need to go through a quantum phase transition. And when that phase transition is continuous, it's what we call a quantum critical point. And experimentally, quantum critical points are rather bizarre because they seem to influence the physics over a huge temperature scale. And here is a color-coded plot of the resistivity in this material, ytterbium rhodium 2 silicon 2, illustrating that it has a linear resistivity near the quantum critical point, but a t-squared behavior either side. These are more conventional metallic behaviors. This linear resistivity, at least in this system, is connected with vicinity to a quantum critical point. And we don't understand the physics of this quantum critical region. Okay? And here is another example. This is an iron-based superconductor, which can also be tuned to a quantum critical point by tuning with phosphorus. And here again, you see a linear resistivity, which interestingly enough is also linear in field. When you put a high field on it, the resistivity becomes linear in field and linear in temperature. So temperature and field can be interchanged in this system. It's as if there's no scale to the problem. So when you put in a scale, that governs the physics. Okay. Here's another example of such systems, which I'm interested in. And so these are all examples of unsolved problems in condensed matter physics: the linear resistivity in strange metals, the strange insulator, the link with quantum criticality and the breakdown of Fermi liquid, and strange metal phases. This last example was actually a strange metal phase, not a quantum critical point, which has unusual physics. And these are just the tip of an iceberg. They are examples which suggest the potential for qualitatively new advances in our understanding of quantum matter. Okay. Okay. The kinds of issues that face the community are, first of all, we're thinking with new languages. So in the modern world of the 21st century, we often use the idea of entanglement. We're familiar with the idea that new types of behavior come from entangling degrees of freedom in new and exotic ways. We have new kinds of phase transition, quantum phase transitions. The problem of classical phase transitions was a major problem in the 20th century, and it involved, for its solution, a fusion of ideas of statistical mechanics with ideas of quantum field theory. Presumably, similar things will be required here too. We probably have new kinds of broken symmetry. We have new concepts such as fractionalization and topology. It would be very unusual if these concepts only apply in the lab and don't without applying also out in the cosmos. Where are the quantum phase transitions in the cosmos? Okay? Where is the quantum criticality? What about fractalization? In the reductionist point of view, you take particles apart and you split them into their smallest components, from atoms to electrons and nucleons, and nucleons to quarks. But in the context of condensed matter physics, you get a reverse phenomena. You start with the microscopic particles, you put them in an interacting environment, and they can break up spontaneously. And we call that fractalization. It's an emergent breakup of particles. And last but not least, the interplay with topology. These are all issues that are central to modern condensed matter physics. Okay? So in conclusion, and perhaps this is the most important part of my talk, I think it's true to say that there are major unsolved problems in the lab that we have to solve. They will require a conceptual understanding of emergent physics in quantum systems, and it would be very surprising indeed if those conceptual principles don't apply to quantum physics as a whole, both in the non-relativistic and in the relativistic setting. Okay? So I want to turn to one of these, as in the past, phenomena in the lab, the cosmos at large will be related. I don't know that for sure. That's part of my religion. Okay? I believe that to be true. Okay? Right? Okay. So I'm going to focus on one aspect of this little list here, which is fractalization, which is something that we've become very interested in. Okay? And I want to tell you about fractalization. And before I do so, I thought I would also talk about quantum criticality, but I don't have time. So I just wanted to flash up this one picture of 3 different systems on the brink of localization. 4D systems, the cuprate superconductors, the 4D iron-based superconductors, and this 4F cerium system, this 115 superconductor. And in each of these, by tuning some parameter, it's typically doping or perhaps pressure, one can tune between a localized or partially localized phase, which has some form of magnetism, into a delocalized phase. And as one tunes through, one observes some kind of quantum critical point, and in the vicinity, new phases quite often, and selectively in these examples, superconductivity developing. Okay? And so around these quantum critical points, new phases seem to develop. And so presumably to understand the new phases, we have to understand the quantum criticality at the beginning. But maybe we also need to think about new ideas for the description of ordered phases. And so this is a major problem for the 21st century. We desperately need a unified conceptual description of quantum criticality and novel phases. Okay, so I want to talk about order fractalization, and this is work I've done with a Rutgers postdoc, Yasha Komajani, a former Rutgers postdoc, Anna Toth, Premi Chandra as well. And this is the archive which we put down recently. So one of the major concepts discovered in the 19th century was the concept of order. And order is the notion that when you go through a phase transition and matter changes its form, that you can parameterize that order with a macroscopic quantity we call the order parameter. For example, the magnetization in the case of a ferromagnet. But in the case of a superconductor, a mysterious field, the psi field, which was initially proposed as an object which nobody knew where it came from, which later acquired significance in terms of the condensation of Cooper pairs. But Landau in 1937 proposed the concept of an order parameter as a way of describing broken and linking the formation of new phases with the breaking of symmetry. And the idea is that the world we live in, the microscopic Hamiltonian, has a plethora of symmetries, but that at some point those symmetries can be broken spontaneously, and when they do so, an order parameter emerges which is not invariant under those symmetries. It changes. For example, in a superconductor, the order parameter has a phase, and that phase breaks a symmetry, in this case the conservation of particle number, a gauge symmetry. And so each of these, although the energy is independent of changing the phase of the superconductor, the ground state picks a given location. Okay? And this is then a spontaneously broken symmetry. In an Ising system, it's either up or down. Okay? And then there's another concept which is essential to our extension of the idea of broken symmetry to quantum matter. And this is the concept of off-diagonal long-range order. It's very important because, for example, in a superconductor or in a superfluid, the order parameter is the creation operator of a pair of electrons or of a boson. And the physical states of the system might have a well-defined number of particles. And so that object cannot have an expectation value in one of those states. Nevertheless, if you look at the correlation functions of that object at very great distances, then you find that it goes to a constant, and that constant is just the factorization of the order parameters. Okay? And so this factorization of correlation functions was studied extensively by Yang and was really a culmination of trying to understand some of the exotic mean field theories, such as BCS theory, in the late 50s. And we call it off-diagonal long-range order. And nowadays, we treat it as an integral part of our understanding of statistical mechanics. If you want to look for long-range order in a Monte Carlo calculation, you look at the correlation function. And so these concepts, the order parameter is a static property. It's a property of the ground state. In electronic matter, we have to form one of these bosons to have it condense. And to do that, we have to combine fermions and make an even number of fermions, because only when you have an even number of fermions do you create a particle which is even under exchange. Okay? And so since an order parameter is a boson involves pairs of fermions or even numbers of fermions. And this has an interesting consequence. It means that since we must combine even numbers of fermions, the order parameter must have an integer spin, must have a charge that's a multiple of 2e. Okay? And so, bizarrely, our order parameters behave in the same way as bosons in relativistic matter. They satisfy a spin statistics theorem. Okay? And yet they shouldn't do. Why should they satisfy that? There's no Lorentz invariance in quantum matter in the lab, and so it doesn't have to satisfy a spin statistics theorem, but yet in the mechanisms we know and understand, it does. Okay? Okay? So half-integer order parameters are impossible according to our current understanding of broken symmetry in electronic matter. They're literally impossible. Okay? On the other hand, we've been taught another lesson in recent years, and that's the lesson of fractionalization. And we are, in condensed matter physics, in an era of fractionalization. Unfortunately, the country as a whole is also in an era, a different kind of fractionalization, which I won't talk about here. But in the concept of many-body physics, fractionalization is the fact that quantum operators can create pairs of excitation. So when you flip a spin inside a magnet, normally you would create a magnon. But in low-dimensional magnets, when you flip a spin, you can create pairs of half-integer objects we call spin-ons. And this actually occurs in the Heisenberg chain, the spin 1/2 chain. And on the left-hand side here, you see the measurement of the spectrum of spin fluctuations in a one-dimensional antiferromagnet. On the right-hand side is a theoretical prediction, and they match up beautifully. And what I want to draw to your attention is that when you flip a spin, you create a continuum of excitations. And that can be understood in terms of when you flip a spin, it breaks up into two counter-propagating spin 1/2 excitations we call spin-ons. In some loose sense, the spin factorizes into a product of creation and annihilation operators. Okay? There are other examples, but before I go on, notice that this is an excited state property. To see this fractalization, you have to look at excitations. Okay? It's a dynamic property, and it exists in the dynamical correlation functions, the response functions of the system, and it involves time. Here's another example of fractalization, the Kitaev honeycomb model. It's a 2D model, and it has this funny property that it has spins that interact in 3 different directions, either with their x direction, y direction, or z component. And this is an exactly solvable model, and you can solve it by writing the spin operator as a product of Majorana fermions. This is the way that Kitaev made the substitution, and he was able to solve the problem exactly. Amazingly, and I don't think even Kitaev would have imagined this, we have systems that actually realize his exotic model. You can mess with them, and this is an example, I think, of ruthenium trichloride, and it's an antiferromagnet, but when you put a magnetic field on it, you can destroy the magnetism with its zigzag order and enter the Kitaev phase. And when you do that, you find that it exhibits a quantized thermal Hall constant, which was first predicted by Kitaev, and this is confirmation of the Majorana edge modes that run around this state when you put a magnetic field on it. So this is a very nice example because you can solve it exactly theoretically, and you can measure it exactly experimentally, and it confirms that spins can fractionalize in exotic ways. Okay? And as my last example of fractalization, I want to mention exactly those quantum critical points that I talked about before. We don't understand these quantum critical points, and this has led to the conclusion that they must be described by a physics that's different to that of conventional quantum classical criticality. One way of solving criticality would be to just add the dimension of time into a Wilsonian description of broken symmetries. And when you do that, it turns out you can't understand the physics that's going on in these systems. And so it must be a different kind of universality that's taking place. And one idea that's been proposed, which has been partially confirmed in the context of magnetism, is that the order parameter that's emerging in these systems fractionalizes at a quantum critical point. And this idea of deconfined criticality has been proposed by Senthil, Vishwanath, Balint, Sachdev, and Fisher. It was motivated by these exotic metallic quantum critical points, but it's been confirmed in the context of frustrated magnetism. Okay? And it's purely a hypothesis, but it raises a very interesting question. If order parameters can fractionalize at a critical point, then is it possible that if you go into the ordered phase, that the fractionalization will continue? Or does the fractionalization occur exclusively at the quantum critical point? In the model of Senthil et al., what happens is that another fixed point takes over and you get a valence bond solid forming. Okay? But if that fixed point weren't there, then there would be perhaps the possibility of actually condensing these spin-ons. Okay? And this is part of a motivation. Oh, before I do that, let me mention another aspect of fractalization, which has long gone unexamined, which is the fact that in heavy electron systems and in so-called Kondo lattice systems, we have local moments which kind of dissolve and form delocalized electrons. And I'll come back to that. They develop a fractionalized, they form heavy electrons, which can be regarded as a fractalization of local moments in 3 dimensions. Okay, so where are we going? Yes, okay. So this then leads us to conjecture that order might fractionalize, okay? And if it fractionalizes, then presumably some aspect of this dynamic physics remains in the off-diagonal long-range order. And as far as we can see, when order fractionalizes, it leads to a kind of long-range order, not only in space, but also in time. It requires an extension of off-diagonal long-range order into space-time. And it now liberates us from the slavery of the spin statistics theorem, which shouldn't apply in condensed matter physics, and it means that half-integer order parameters become possible. I want to tell you a bit about our attempts to confirm this conjecture. Okay? Before I do that, let me give you some of the motivation. Okay? Here's one of those models in condensed matter physics that we can't solve. Okay? It's very, very simple. It involves electrons buzzing around, and the local spin density of those electrons couples antiferromagnetically to the local moments at each site. This is known as the Kondo lattice model. My friend Andy Millis calls it Platonic Kondo lattice model because, of course, in electronic matter, these spins come from electrons originally. But they might come from any origin. They might be nuclear spins, and the physics would be the same independent of what their origin is. Okay? And that's important because we know what happens to this model. In fact, we even have a theorem as regards its physics. What basically happens when you put these spins into a conduction sea is that they actually entangle with the conduction electrons, and their spin is then injected into the spin wave function of the system. And as a result of that, there are now more spins around to form the Fermi sea, and the Fermi sea enlarges. It's a kind of many-body ionization because you have more electrons at the end than you started with, and the only way to understand that in terms of neutrality is to think of each local moment as having split up into a negatively charged electron and a background singlet, which you have to count as being positively charged. Okay? And here's what happens when you add a whole bunch of these local moments into a conduction sea. Of course, we don't ever do this thought experiment. We start out with systems that have local moments. We know they're there at high temperatures. We cool them down, and we discover they entangle to form a heavy electron sea. We call these heavy fermion materials. Okay? Now, it turns out that, in fact, we can actually prove that if this ground state is a Fermi liquid, then the ground state has to have an enlarged Fermi surface. In the old days, the traditional view was that the spins here came from electrons, and in fact, this model was the low-energy version of another model called an Anderson model, and so you're just recovering the electrons that formed the spins. Okay? But actually, the modern view is that this model actually describes the fractalization of the local moment into a charged Dirac particle. When I say Dirac, I mean complex fermion, okay? And so this is literally what happens to the spin. It fractionalizes and injects its spin into the conduction sea and somehow becomes a charged object, okay? And there is actually a theorem due to Ishikawa that the Fermi surface expands to count the number of local moments, spin 1/2 local moments. Okay, this theorem was proved using a very beautiful topological argument that I don't have time to go into. Okay, and we can even see this delocalization in cerium, rhodium, indium 5. If you put pressure on it, you can induce it to go from an antiferromagnet into a paramagnet, and when it goes to the quantum critical point, you see new Fermi surfaces emerge due to the delocalization of the local moments. Okay. This raises an interesting question. If we're so bold as to think of these systems as spin fractionalized systems, what other kinds of fractalization are possible? And this isn't just an issue that is important for these particular materials, which are rather exotic. You're not going to be driving your car driven by this new material, uranium ruthenium to silicon 2. But if you look at it, it has interesting properties. This particular material has a weird phase transition discovered 30 years ago, and the condensed matter community have been firing neutrons, electrons, X-rays, STM, everything at this material. They know it undergoes a phase transition, but they haven't been able to discover the order parameter. Okay? And so we call it hidden order. But one of the weird things about it is that the expanded Fermi surface in this system, which come from local moments on the uranium atoms, has electrons which have an Ising anisotropy. Namely, they only respond to a magnetic field in one direction, the C-axis, and this is a measurement based on quantum oscillations that shows this Ising behavior. And we don't understand these Ising electrons because Ising behavior is typically a property of integer spin quasiparticles, okay? But electrons are half integer spin objects. And so if these are integer spin quasiparticles, then they must have acquired half a unit of angular momentum. And the only way that would be possible would be if the order parameter that involved mixing them, hybridizing them with a conduction sea, was itself a spinner. As if the multipoles in this system have broken up into a half integer order parameter. Okay, that's just one example, and we wrote a paper on that. We made a prediction. The prediction was not verified. So the theory is probably wrong, but the spirit of the theory may still be right. And here's another example. This is neptunium, palladium 5, aluminum 2. This material was discovered by Dai Aoki when he, you have to be at a pretty high security lab to work with neptunium. When he tried to synthesize something in a palladium crucible, and the neptunium interacted with the crucible. And out of it came some stuff. And when he cooled it down, he discovered this stuff had a Curie Weiss-like susceptibility, was very anisotropic, a signature of local moments, but it actually goes superconducting at 5 Kelvin. And these local moments disappear when it goes superconducting. They entangle with the conduction electrons. And so this system goes from a Curie paramagnet directly into a superconductor. And so this looks as if, since the local moments are disappearing as it goes superconducting, that again the spins are fractalizing at the phase transition, suggesting the fractalization might be part of the phase transition. Okay, so putting these things together, we have 3 different examples of fractalization here. One pressure-driven, which doesn't break any symmetries, but one in which we get some kind of superconductor, and one which get some kind of weird hidden order with Ising quasiparticles. And so these motivate the conjecture that order can fractionalize. Okay. Okay. So I'm getting to the end of my talk. I just want to spend a little bit of time telling you how we try to demonstrate this idea. Okay? A proof of principle. Can we come up with a model where we're sure that the order parameter has fractionalized? Okay? And this is a little bit technical, but let me just tell you a little bit about it. To make this work, we have to think about how electrons feel order. When an electron travels through a ferromagnet, it feels the Weiss field of the surrounding electrons. And the way it feels it is that as it scatters into many body states. These many body states propagate and then they re-emerge as an electron. And the amplitude for that process is described by something called the Dyson self-energy. It's exactly the same as the self-energy we use in quantum electrodynamics to describe the fact that an electron can emit a virtual photon. Here, an electron can emit a virtual particle-Hall pair, a spin flip or phonon, and then come back together again. And this is an amplitude which, in a broken symmetry environment, on length scales beyond the coherence length of that superconductor, typically behaves as a scattering potential, such as a magnetization, okay? And these broken symmetries are like typically like local scattering potentials, and they are described by an irreducible representation of the broken symmetry, okay? And that's our current understanding of broken symmetry in electron matter, okay? Order fractalization would mean that order parameter breaks up into a product of order parameters. But in order to see that it's broken up, you'd have to separate these 2 points by a large distance, longer than the coherence length, or a large time, longer than the coherence time. And for that to be true, you'd have to have some low energy excitation that propagated from A to B. That low energy excitation would have to be a fermion, because you're sending a fermion in. And so in order that order fractalization occurs in a fermionic system, you have to have the formation of low energy fermions, new emergent fermions, okay? And this would then mean that the self-energy factorized it and became a reducible product representation. Okay, there's evidence for this occurring. So if this occurs, order fractalization is linked to the formation of fermionic bound states. And these have been seen in some simulations, and the idea of fermionic bound states have also been introduced in attempts to understand the pseudogap phase of high-temperature superconductors. Here are some simulations that seem to see a pole in the self-energy developing in cluster dynamical mean field theories, and these authors, Sakai, Civelli, and Imada, call these excitations dark fermions. Okay. And so this is the basic idea, the idea that 3 fermions can come together and they can bind, but they bind in a way that breaks symmetries, which means that these 3 fermions, when they bind, they carry a set of quantum numbers which we can partition into the lambdas and the alphas, which describe different symmetries, okay? And so the idea is that this bound state splits up into a fermion that carries one subset of these quantum numbers, leaving behind, this is the dark fermion, a kind of order parameter corona, a field that carries the residual quantum numbers. And it's this half-integer object that describes the order fractalization, okay? So we spent some time trying to look into this idea, well, just summarizing, this is the conjecture. I've just got a few minutes. Let me tell you a little bit about how we try to show that this idea can work. And it looks to me like my slides are reproducing. Okay, so let me remind you about how broken symmetry was first discussed back in the early 20th century. And the idea, which was invented by Curie and Weiss, was the following. First, take a local moment and bring in a magnet and polarize it. So understand how an individual spin responds to a magnetic field, okay? That's induced broken symmetry. You've broken the symmetry with an external field. And then, if you take that guy away, then the broken symmetry of one site provides a Weiss field for neighboring sites. This feedback, this positive feedback, allows the broken symmetry to survive the removal of the symmetry breaking field. And that's called the Weiss molecular field. And so if we believe that order fractalization can occur, we have to find a way of providing a fractalization magnet, of inducing it, okay? We need to find a model, an impurity model, where we can induce order fractalization with an external field. And one such model, an ideal model, is in fact not just a single spin, but a spin immersed in a conduction sea. Okay? And this is the model that already I mentioned to you fractionalized. And so as a warm-up, we need to understand how the spin fractionalized and how we can see it. We're going to do this using numerical renormalization groups. So here is the model, and it's long been known that the scattering of the singlet that forms in this thing leads to a resonance called the Abrikosov-Suhl resonance. But if you look underneath the Abrikosov-Suhl resonance, the self-energy in this problem must have a sharp pole. This has been predicted based on phenomenological theory and on some gauge theory methods, but can we show it's true using numerical RG methods? Okay, so that's what this is what's predicted using a mean field theory, just a sharp pole. And so this is what we see when we do an exact numerical RG measurement of this self-energy. You see here a sharp pole that shows the formation of this composite fermion, and a background here which comes from the scattering, the residual scattering, the formation of particle Hall pairs. This is due to the Fermi liquid background, okay? And so this confirms the fractionalization, okay? So, and in fact, with this picture, you can understand, make a very simple model of this. What's really happening here is that a spin flip times an electron is forming a fermion. And in this process, because all the quantum numbers of this three-body state are carried by the fermion, it's charged, it carries spin, there's no broken symmetry. But could we see this happening in a way that has this order parameter corona? We went and looked at another model, which is the, okay, this is technical stuff which I won't go into, the two-channel Kondo model. And in this model, this is a very interesting elementary model. It's a spin that's coupled to two different screening channels. And this is an elementary model of a quantum critical point, this system. When you look at the ground state properties of this system, since the singlet can't form in one channel or the other, it actually resonates between the two and forms a quantum critical state. It's a critical non-Fermi liquid, but when you break the symmetry, and the way you can do that is by making one channel stronger than the other, what happens is that the singlet forms in the strongest channel, and you once again form this resonance in the strongest channel. So we thought we'd see if we could see this in NRG. And here is what the scattering looks like in the absence of the channel symmetry breaking. And when you put the channel symmetry breaking in, the one channel develops a pole, and the other one develops a dip down in its form, which actually has an omega squared at the bottom. And so what this tells you is that the self-energy has got a pole, but only in the strongest channel. If you want to write down the form of this self-energy, it's really a projector into the strongest channel. And one way of writing this, which is rather general, is to write it as the product of two spinners that project you into this channel. Okay? And we now know that because this self-energy is a product of two spinners, okay, we have to, and because it has this 1 over omega in the time domain, it means it splits up like this. And so we can separate these two order parameters very far in time. We've actually induced order fractalization. Okay. We can do one more thing with this. We can prove we've got a spinor half order parameter because we can change the direction which we break the channel symmetry and take this thing round a loop in phase space, in channel space, and we can look at the Berry phase it picks up and find it's actually a half integer Berry phase. That's about as far as we can go with NRG, and the rest becomes second guessing. The Weissian stage is when we have to put together approximate theories. If you were to take this idea and take it to a lattice model, then in a two-channel Kondo lattice, there's good reason to believe that this channel symmetry breaking would be spontaneous, and now the spinor would form spontaneously. In fact, and that would now mean that you have off-diagonal long-range order, this factorization. In space-time, the intermediate fermion would now propagate from A to B, would have its own Fermi surface, and would give this singular light cone type structure. Okay, and this has actually been seen in numerical simulations, and we can now interpret it in terms of order fractalization. So this is the speculation. Just want to end up by bringing back to the case of samarium hexaboride. Samarium hexaboride is this very weird insulator, and it shows this resistivity that diverges at low temperatures. It's a typical insulator, has surface conductivity. We can even measure both the bulk and the surface conductivity by doing non-local measurements. This is beautiful work done at Ann Arbor, Michigan, and they can actually measure the bulk resistivity even beyond the point where it's short-circuited by the surface conductivity, and it just goes on up by another 4 orders of magnitude below this temperature here. It's a wonderful bulk insulator, and yet it has tons of excitations inside it. We can see these. We can see it has a large linear specific heat. It has lots of optical excitations. In a magnetic field, it develops a linear in temperature thermal conductivity. It has these quantum oscillations, and these quantum oscillations behave according to the standard textbook Lifshitz-Kousevich theory of temperature dependence of a Fermi surface, which tells us there's actually an underlying Fermi function, and yet it's an insulator. How can you have a Fermi surface in an insulator? You might say, well, it's obviously neutral fermions. How can neutral fermions see a magnetic field? Magnetic field comes from the curl of the vector potential. Electrons couple to the vector potential, and they feel it if it changes in space, but they also feel it if it changes in time, and that's an electric field. And so gauge symmetry forces them, if they feel the curl, to feel the electric field, and yet if these guys are there, they only feel half of it. What are they doing? Okay. And so we've played with the idea that this system might actually have a Majorana fractalization of the spin. I had a lot of fun putting together the theory of that. I won't tell you anything about it now, except to say it's part of a table we've been trying to put together, trying to model the different ways in which spins might fractionalize in Kondo models. In this particular model, what happens is that if the spin fractionalizes as a Majorana fermion, a weird thing happens because the conduction C is a regular bunch of fermions, and you can think of a spin up and a spin down fermion as four Majorana fermions. Each electron splits up into 2 Majorana fermions. But the spin provides 3 Majorana fermions, and so 3 doesn't quite match with 4, and one of the poor d electrons gets left behind as a gapless Majorana band. We think something to do with this idea may explain these neutral Fermi surfaces. So I'm really done now. My conclusions are that the most important, history teaches us that physics in the lab and the cosmos are often intertwined, and that if you want to understand the cosmos, sometimes you have to go and look under your nose, look at the physics that's going on in the lab. I tried to tell you a bit about some of the dark matter challenges of the solid state, and the fact that the inspiration these provide give us a potential for qualitatively new advances in our understanding of quantum matter. I didn't talk about quantum criticality very much, but I did mention order fractalization as an example of one idea that might be helpful in understanding novel phases. Thank you for listening to me.
Are there any questions? Go on.
In high TC superconductors, TC transition temperature is 100 degree Kelvin, and the linearity of resistivity is persists up to 1000 Kelvin. Which phenomenon is more surprising to you and more difficult to understand, or are they related?
So of course, in the modern world of high pressure physics, we already have TCs of 250 Kelvin by pressurizing matter to immense pressures, 100 gigapascals and beyond. So the highness of the TC is not the surprising thing anymore. Although to get that high TC without immense pressures is still surprising, and we don't know whether we could make it go higher. But the linearity of the resistivity, in some sense, is the more fundamental question, because that tells us something about the fabric of the metal we're dealing with is different to what we normally understand. And it would be very strange indeed if that new feature weren't an integral part of the physics of the superconductivity. And so I would say that the strange metal problem is the biggest prize out there theoretically for solving this issue. Yeah.
So this idea of order fractionalization is interesting. I guess normally when I think of fractionalization, I think of the way that you introduced it in terms of a property of the excitations in a phase of matter that does not have an order parameter.
Yes.
For example, fractional quantum Hall.
Yes.
Order fractionalization would be some ways to classify phases of matter which have different types of order parameter. Basically, I'm wondering if you could, is there a connection between the type of fractionalization that sort of was introduced?
Well, so the notion would be that sometimes, in some new sense, that those fractionalized excitations are themselves bosons. And so they condense in some very simplistic way, right? If they then condense, then we'd actually have a road to a half-integer order parameter, a way to circumvent this apparent no-go theorem that we have in our current understanding. So that was the reason that we tried to put this idea together. Yeah.
So in the original Yan's paper, where he proposed the off-diagonal long-range order concept is always related to the flux quantization. And here, for your fractionalized order, is there still a flux quantization there?
Yes. So we haven't thought about these issues. And I'm very hesitant to say, because I've got a fractional order parameter, I'll get a fractional flux coming through. There are, so let me just make an aside on this. The part of the problem is that there's definitely a kind of Higgs physics associated with this. When you fractionalize, you acquire a gauge symmetry, typically. And once you have a gauge symmetry, you have gauge fields. And those gauge fields typically, in an ordered phase, will disappear, will acquire a mass. And so it might well be that as a result of that Higgs phenomenon, you don't get the fractional terms that you're referring to. And so I would be very hesitant to believe that one would actually get charge H over E vortices. But we haven't thought about it in great detail.
Coming back to your big theme of a connection between condensed matter and the larger scale universe. All your condensed matter examples are really highly quantum, but normally when we think at larger scales, we're in the classical regime. Do you think that that dichotomy has been overemphasized? You didn't mention ADS-CMT, where you have a classical black hole mapped onto a quantum system. What are your thoughts?
The ADS-CMT is a marvelous speculative idea. And if it could be made into a tool which the engineers of this world can use, like myself, then I think it would be a wonderful breakthrough. But at the moment, it's still a speculative tool. But you mentioned also the fact that the large-scale world is classical. And so presumably, the dark matter problems of the universe are probably classical in some sense. But nevertheless, what does classical mean? Classical might mean some emergent classical physics. After all, a superconductor is an emergent classical piece of physics. And so I don't know, in some sense, the most marvelous thing about the world we live in is that classical mechanics is the ultimate consequence of quantum mechanics. It is the most dramatic and wonderful thing that phase coherence comes together to produce this solid world that we live in with all of its broken symmetries. And so, so yes, it must, I think the large-scale world is eminently classical. But quite what that means and whether you can get new kinds of classical physics emerging from the quantum scale is an open question.
All right, let's thank Piers again.